currently in the Discovery Gallery of the GDC. All sorts of really cool things around here. Won't spin around too much to make you barf. I'll tell you one thing that will make you barf is this thing here, the space capsule. You climb in here, you spin yourself around using that steering wheel, so you sit your butt in one of these chairs, spin yourself around, and then on the G meter, which is just down the back there, you can record how many Gs you're pulling. The record is about 4G, done by two really big blokes. And once they'd slow down and finish it, they staggered out that back door into the bush, barfed up their lunch. It was awesome. Let's go for a ride. Here we go. Climb in. Okay. Look on the G meter. Start spinning myself around. There we go. You can see up there it's actually starting to get. Oh, this is not good. I'm feeling sick already. As you can see, outside is going around quite badly. Oh, no, I've really got to stop. I'm going to barf. Got up to about 0.25 of the G, and now I'm not feeling good. Oh, that's bad. What if I spin the other way? No, that's not helping. Anyway, I'm going to stagger out. I just remember now why I hate going on rides. Oh. I feel like I'm going to barf. The whole reason why we're here is because of something called AGO. Now, AGO is the Australian International Gravitational Observatory. It's looking for all these elusive things called gravitational waves. Now, Albert Einstein first came up with these things called gravitational waves back in 1915 when he wrote his paper, The General Theory of Relativity. Now, after saying that matter changes the shape of the universe and it's the shape of the universe that tells matter how to move, he also said, or he postulated the existence of these gravitational waves, these ripples through the fabric of space-time. The same way that water ripples when you drop a pebble into a pond, it causes these ripples to emanate out from that impact point. Except this is not caused by pebbles dropping into the cosmic pond, it is the interactions of two black holes or stars exploding or whatever. He also said in that same breath that we'll never ever be able to detect these elusive gravitational waves because they are so infinitesimally small. They're about the thousandth of a diameter of an atom. So of course, to detect something like that, you need exquisite precision. And they have made this. They've made this with two large laser interferometry gravitational observatory. That stands for LIGO. Now, of course, LIGO is the two big detectors in the United States. LIGO Hanford and another one called LIGO Livingston down in the southeast part of the United States. These are massive laser gravitational wave detectors. They've got baselines that fire lasers down these vacuum tubes that are 4 kilometers long, and they are exquisitely precise. You can see these really long baseline arms that extend 4 kilometers at right angles to each other. And within those right angles and within these tubes, all the air is pumped out. The high-powered laser is fired down through these tubes, and the laser travels back along itself, back to the main laboratory where there's a detector. And any change in the light of the laser can signal a gravitational wave coming through. So back on the 15th of September 2015, they actually detected gravitational waves for the very, very first time. It was one of these amazing discoveries in science, and it proved Albert Einstein right. Now we've got something like that here at AGO, the Australian International Gravitational Wave Observatory, except the baseline's here only 80 metres long, but hopefully they're going to be extended out to 4, possibly even 8 kilometres in length, which make it the biggest gravitational wave detector in the world. I'm going to show you a really cool model that we've got here at the GDC, and it actually shows you how a laser gravitational detector works. So here is our model of a laser interferometer which tries to detect gravitational waves. This would be the main laboratory. Laser goes through the beam splitter, down one arm, down through this arm down here, to this thing down here called test mass that stops any vibrations from ground or trucks kilometers away, transferring the vibrations up, which could give us a spurious reading. So the laser hits the test mass, goes back through the tube, through the beam splitter, Okay, the second arm goes along through here to its own test mass, back along the beam, comes back to the beam splitter, and then it gets split off again through this diffraction grating to form an interference pattern at the back. Watch what happens when I apply pressure to the bench. And I'm only just pushing that lightly. See how it's moving around? And if I give it a whack, light tap, it causes the interference pattern to move. But imagine this on scale so much larger, like kilometre long baselines and higher powered lasers. And with this, you can actually detect a gravitational wave. Absolutely incredible.